Topic A, Experiment 2, Injection Molding and Bending Test. Objectives: operate a heat press machine for injection molding dog bones tensile samples, and perform 3 points bending test and interpret the data. By observing the behaviors and analyzing the data, students will learn: first, the comparison between the tensile and bending strengths, and second, the time-dependent deformation behavior of the material. Background: injection molding. A schematic cross-section of the apparatus used is illustrated in Figure 1. The correct amount of pelletized material is fed from a feed hopper into a cylinder by the motion of a plunger or ram. The material is pushed forward into a heating chamber to melt and form a viscous liquid. Next, the molten plastic is impelled through a nozzle into the enclosed mold cavity. The pressure is maintained until the molding has solidified. Finally, in this process, the mold is opened, the piece is ejected, and the process is complete. Examples of thermoplastics are ABC, polyethylene, and PVC. These materials have unique chemical properties to let them be remolded and recycled without negatively affecting their physical properties. That makes them ideal for injection molding. 3-point bending test. The 3-point bending test is a classical experiment in mechanics used to measure the Young's modulus and the deflection strength of a material. The beam specimen is loaded in a simply supported condition with a point load at the center. To perform the experiment, the beam specimen is loaded in the simply supported condition with a point load at the center. The bending stress of the beam can be calculated as the next equation: 3 times PL over 2 times B squared H, where P is the point load, L is the space length between two supports, H is the height of the beam section, and B the width of the beam section. Plastic hinge. For testing a ductile material using 3 points bending test, forming plastic hinge is one of the common failure mechanisms. When beam is slightly loaded, the beam specimen starts to bend with only the elastic deformation of the material over the cross-section. The stress distribution over the cross-section has a transition from the maximum compression at the upper face to the maximum tension at the bottom face with zero stress at the neutral axis. This shape of the stress distribution over the cross-section is assumed for using equation 1 to calculate the bending stress. Later, when the load increases and the beam starts to be plastic deformation, materials close to top and bottom faces start to yield. This makes that the shape of the stress distribution deviate from its original shape, making that equation 1 overestimate its actual stress value. Eventually, when the load gets high enough to make all the materials over the cross-section to yield, the entire cross-section starts to lose its stiffness and behaves like a hinge. Creep test. This is a simple test. Basically, a material is loaded for a long time. If the material deflects with time, it is said to creep. The loading period may be a few minutes or a matter of days. At elevated temperatures, steel undergoes creep as evidenced by distorted and twisted structural members that remain after a fire. In service, creep sometimes occurs very slowly and may not be apparent even after a matter of months or even years. Don't forget to consider that plastics are susceptible to creep, especially thermoplastics, when they are loaded above their glass transition temperatures. A creep test may be conducted with the same configuration as Figure 2. In this case, the bending stress due to the applied load will be constant, but the deflection or strain will increase with time. We have mentioned the time in our calculations. Whenever an equation is in function of time, Obviously, it causes a result change with time. For an elastic beam, the longitudinal strain at the top and the bottom of the beam is given by the equation that we have here. 6 times delta TH over square L, where epsilon is the longitudinal bending strain in the upper and lower phases of the beam as function of time, and delta T is the deflection of the beam as a function of time as well. In this case, the units are in millimeters. The creep modulus represents the modulus of a material at a given stress level and a temperature over a specified period of time. Dividing the stress by the strain and expressing the deflection and the modulus as time-dependent variables gives a time-dependent creep modulus. This is an example of the plot of creep strain versus time. The other name that it receives is the creep curve. It's easy to identify three main parts of the curve. The primary portion is the curvilinear portion. Secondary creep is defined by the linear portion of the curve. And tertiary creep is associated with the failure and the development of cracks in the material. Experiment steps and procedures. Use polyethylene pellets as the raw material and use the heat press for injection molding to manufacture the polyethylene dock bond samples for tensile test. Step 2. Measure the dimensions of the polyethylene dock bond and beam samples. Step 3. Perform the tensile test for the tensile samples and the 3-point bending test for a beam sample to measure the ultimate tensile strength and bending strength using the equation 3. Step 4. Apply a constant load that gives 25% of the deflection strength and record the deflection from the dial gauge at the time period in the table below. Plot the strain versus time graph using Excel.